So, here we go. We are gonna continue applying integration techniques that we have learned. So let me, I have my OneNote open. Let's go into, what's it called? Notes mode. There we go. Okay, that's not working. There we go. That's what I wanted. Okay, and 1 second, I need to move my windows. Okay, let's minimize that. Move this over. There we go. Yes. Okay, so what have we been talking about? So like I talked last time, we've been learning about integration. The easy part, as you can see here, the part that I've put the little thing in blue, is once you have your integral using the fundamental theorem of calculus to find the antiderivative and calculate it. The hard part is the setup. So usually what you start off with is this idea of how you're going to approximate solving the problem, and then you want to turn it into a Riemann sum, which you then take the limit of, and that tells you what integral you need to solve. And we talked about how what the interpretation of the Riemann sum changes depending upon what you're doing. So for instance, you know, that f of x times delta x originally was the area of rectangles. Then eventually we figured out that f of x times delta x could be the length of a line segment, right? You add up areas of rectangles to approximate an area, you add up lengths of line segments to approximate arc length, you add up surface areas of frustrums to approximate surface area, and so on. Okay, and then boom, you get your answer by taking the limit, which turns into a definite integral. So last time we took this idea and we used it to calculate mass given density. So we start off with this idea of linear density, that the density just depends upon some distance on the x-axis. Right, so then we use that to calculate mass for something. Right? We had this little rod, we broke up the rod into pieces. Right, that's that approximation. We calculated the mass for each of those little pieces of the rod, and then we were able to solve an integral to come up with the total mass of the rod. Okay, now what we left off last time was we talked about radial density. Okay, so radial density means like we have this disk, so we're just going to assume that, like, we're dealing with a hockey puck basically, and we're assuming that the disk is thin enough so we can think of it as a 2D object. And then what our assumption was, well, the density is in terms of unit area as opposed to unit length, right? Because we're dealing with an area now, not just a one-dimensional object. And that the density only depended upon the radial distance. So in other words, as you move along the radius, that determines the density at the point. Right? So I have these concentric circles here. Each of those concentric circles has the same density. And so I'm just like sort of rolling through this so we can get caught up to where we were last time. We know that mass is equal to the density times the area in this case. So we have our circles here. You can see my concentric circles. That's the equivalent of how we broke up our line segment into equal parts, right? So we have these concentric circles that are a delta x getting bigger by delta x every single time. Right, so I looked at one of those circles, right? You can see it has all little hash marks. And the idea was, okay, so if we want to calculate the mass, we're going to multiply the density by the area. So we calculated the area of that little annulus, the ring. Right, that's why I have A3 minus A2, right? You took the pi r squared minus pi r squared. And we went through the calculation, and we noticed that pi x3 squared minus pi x2 squared, you could factor out the pi, so you got that. And then you notice, looking at these, that x3 minus x2, that's the distance between the 2 points, that was just delta x. Right? We always define that to be delta x. So I made that change right there. x3 minus x2 was delta x. And then looking over at x3 plus x2, I have this like really horrible drawing over here, and I'm going to rewrite it so that it looks nicer. Because I realized that might not have made any sense yesterday. So Here's a circle. Let's draw another circle too. Draw a bigger one. That was so beautiful. Okay, so here are my two circles. The smaller circle, oh, too thick. The smaller circle has radius x3. The larger circle has radius x4. Alright, we're interested in, let's put in red, we'll like mark it up. We're looking at this thing. Okay, so we're interested in that stuff. Okay, so looking at this radius, okay, if you look at all the points on this inner circle, because we have radial density, what can you say about all of the points on this inner circle? Like I'm putting little tick marks on them. What do you know about all the points on that inner circle? What do they have that's the same? Well, they do have the same distance from the center, but more importantly, they have the same density, right? Because the density only depends upon the radial distance. So there's some density right there. Now, if you look at all the points on the outer circle, what do they also have the same? That's the same. Because they're all the same distance from the center. They also all have the same density. Now, what we want is we would like to know, let's type this right here. How should we estimate the density in the annulus, in other words, the ring? And we came up with an idea. If you wanted to say like, well, the density is, obviously the density starts at some value on that inner circle and changes slowly to some value on the outer circle. What's the value we should use to estimate the overall density for the whole annulus? What was the idea I came up with last time? Yeah, the midpoint, right, exactly. So the idea was like, okay, well, there's some value between x3 and x4, and we'll call that x star. So you have that green circle right there. That green circle is going to have radius x star. It's the midpoint of x3 and x4. So x star equals the midpoint of x3 and x4. And last time we discussed, if delta x goes to 0, x3 and x4 are going to get closer and closer to each other. So in other words, what are both of them going to approach? The midpoint value. That's what this is saying right here. So if delta x, the distance between the successive points, becomes smaller, you can imagine that like those white lines, they're going to move like this, right? The inner white line is going to move out. The outer white line is going to move in, and what are they both approaching? The green line in the middle, which is the midpoint. So in other words, both of them will become equal to x star. So because of that, x3 plus x2 ends up being equal to 2x star over here. Holy shit, burrito. Okay, I'm just going to quickly let him out because I know he's just going to harass me if I don't. So just give me a moment. Okay, I'm back. Okay, so you look at that formula right there, and you can rewrite it as 2. Oh man, I'm gonna mute you because I think you're talking to someone. That was sort of funny though. Someone's gonna be paying for it later. I totally feel that sentiment. I feel like that many times a day. Sometimes when I'm dealing with people, I'm like, oh man, you fucked with the wrong person today. So anyways, it's cool. No, it was actually humorous on my end. Let them know, yes. It's not good to bottle up your feelings. So anyways, I'm sorry. It was. I understand you're probably having a difficult time. It was just sort of hilarious how like I came back after pottying burrito and that's what I heard. And I was like, whoa! I'm pretty sure that was not for me. So anyways, we get this formula which says, okay, the area is equal to the circumference of the midpoint, the circumference of the middle circle times the distance between the two outer circles. Okay, so why did we care about this? Why do we care about the fact that that ring there has an area equal to the circumference of the midpoint circle times the width of the outer circle? Well, because mass is equal to our density times the area, and we're like, oh sweet, the area is 2 pi, the circumference of the midpoint circle, and times the width, the distance between the two outer circles. In other words, 2 pi x star times delta x. Okay, which means our total mass approximately is going to be equal to the sum of that area times the density function. I just rewrote the terms around a little. And then you realize, well, okay, well, instead of approximating that total area, I can take the limit of it, which will give me a, what's it called here? A definite integral. So if you want to find the mass of this object, which has some given radial density, you can simply integrate 2 pi x rho x dx from 0 to r. Boom. Where did that come from? All that work we did about breaking up your your circle into those like different disks and adding them together. Okay, so we're gonna take this idea and we're gonna like apply it to some cool stuff today. Or we're gonna basically keep doing what we've been doing and apply it to another physics concept. Okay, so today we're going to talk about work done by a force. So let's get some terms here. Wait, I'm trying to move that stuff. There we go. Okay, so everyone's probably, let's talk about what is a force. So everyone might recall, hopefully, the force equation, which is force equals mass times acceleration. So acceleration is something which changes the velocity. So acceleration is the measure of velocity change. Right? Remember how like velocity is the change in displacement? Likewise, acceleration is the change in velocity. So in other words, when you accelerate something or decelerate something, you're changing the speed at which it is moving. So if we talk about a force is whatever it is that makes things speed up or slow down. Right? So force tells you if you take some object with a given mass and you change its speed by a certain amount, that's what a force is. So let's write that down. So what is a force? Well, you get F equals ma, but more importantly, force is the measure of taking an object of mass m and changing the velocity by some amount, i.e. accelerating it. So you can think of force as basically like you push or you pull some object. Right, because it makes sense when you push or you pull something, you're influencing its speed, and ultimately, like, you have to push harder for things which are lighter, and you don't have to push as hard for things that are less light. Right, so the force you apply depends both upon the mass and the amount by which you change its velocity. So actually, this is a good time to talk about the units involved in this, because this is something that usually like screws with people. Okay, so you have to remember that force is a mass times an acceleration. So let's talk about the good old imperial system. Does anyone know what the measure of mass is in the imperial system? No, oddly enough, the measurement of force is pounds. No, that's the metric system. We're talking about the imperial system. The imperial system is, our colonizers, the English. Okay. Now that's energy. So, interestingly enough, mass is measured in something called stones, I believe. So when you talk about I weigh 160 pounds, you're not talking about how much mass you have. You're talking about, slugs. Yeah, my bad. It's not stones, it's slugs. So technically, when you say that you weigh 160 pounds, you're saying that the force you exert on the earth is 160 pounds. That is not how much mass you have. Mass is slugs, which is weird. Okay. What's the measure of distance in the imperial system? Miles, light years, we'll use feet. You can use feet, inches, miles. They're all like defined in terms of each other. But we'll use feet. Okay, so why am I bringing this up? Because you can exert a force, and usually you exert a force over a period of time. So there's a concept called work. Work is exerting a force over a distance. So does it make sense? Because a force is a push or a pull. If there's some object and you're pushing it, you'll push the object like 10 feet. You will exert a force over some distance. Okay? So if we're talking about the imperial system, work is force times distance. So if we're in the imperial system, force is measured in pounds, and distance is measured in feet. So the measurement of work is the so-called foot-pound. Because you're exerting a number of pounds of force over some distance of feet. So work is measured in the foot-pound. Yeah, this is why we like this. This is why we like the metric system. Because like doing all these calculations in the imperial system is like, holy shit. So like if you exert 5 pounds of force over a distance of 3 feet, you would have done 15 foot-pounds of work. Let's write that down. Let's do it over here. You'll see how like ridiculous this sounds right here. So let's say that you exert 5 pounds of force over a distance of 3 feet. That is 15 foot-pounds of work. It's that weird, the emoji. Right? Does that make sense? Like you can imagine there's a box and you're pushing it with 5 pounds of force and you push it for 3 feet. We would say at the end of that you did 15 foot-pounds of work. Okay. So now let's talk about the metric system. Okay, what do you measure mass in for the metric system? Yeah, kilograms or grams. Okay, what do you measure distance in? Meters. Let's actually write meters. Okay, so what do you measure force in? Does anyone know the measurement of force? Newtons, yes. And you can actually break this up because, yeah, that's what I was going to talk about. So force is measured in newtons, and what is force? Force is a mass times an acceleration, and we know that mass is kilograms, and we know that acceleration, so acceleration we know is distance over time squared, and the measurement of distance is meters, and we know that time squared is second squared. So newtons are actually kilogram meters per second squared. So it's actually good that you, I highly recommend after today you go back and think about this. So force is a mass times acceleration. Mass is measured in kilograms. Acceleration is distance per unit squared time, which means meters per second squared. So newtons are meter kilograms per second squared. Now, we do this again. Work equals a force times a distance. The force is the newtons. The distance is meters. A newton is a kilogram meter per squared second times a meter. So apparently, what's the measure of work? It's kilogram square meters per square seconds. Or kilograms times meters squared divided by seconds squared. There's actually a special name for this unit. Okay, so just like how the Newton is what we define to be kilograms times meters divided by seconds squared, we have a name for the measure of work. The kilogram times meters squared divided by seconds squared is called the joule. named after a famous French physicist. Yeah, like Joule pods. The Joule. I guess like a really weird intersectional meme would be like saying like I'm gonna hit my work. The joke being that work is measured in joules, and joule sounds like a Joule pod, so it sounds like I'm gonna hit my Joule. But only people who use Joule pods and know a lot about physicists would get it. So I think the number of people who would find this funny would be like infinitesimally small. But you know, that's what happens when you're really educated and depraved, I guess. You know, no one really gets your jokes. Thank you for the LOLs in the chat. I appreciate it. Okay, so you get this joule, which is a measure of work, and work. So the joule is a measure of energy. So does it make sense? Like when you do work, when you push on something over a distance, you expend energy. So work is all about the amount of energy spent to accomplish your task, which is exerting a force over a certain distance. So we're going to write this. So work is exerting a force over a distance, which is expending energy. So it makes sense that your measurement of work is just a measure of the energy spent. I'm like having a hard time saying that. Which is why the joule, the measure of work, is the measure of energy. Woo! Okay. Making sense so far? With the units, this hopefully will help when we actually do the problem, because you'll see where all the units come from and why you do this. Okay. So let's say that you have a force function. This big F is not the antiderivative, it's force. And what we have going on here is that my force depends just on some distance. So my force depends just upon some distance from some point. That's true, but I'm not going to usually you put a little vector arrow when you actually have a vector function. So it possibly could confuse more. But I totally get why you would think that, yes. Is this related to a previous concept? We'll see in a moment how it is or isn't. But let's say that you have a force function and it depends only on distance. And the common model for this is a spring. So let's say you have like an anchor right here. You have a block. And attached to the block, you have a spring. Okay, does it make sense that your spring has some natural, springs they resist being compressed and they resist being expanded, right? So let's say that this is the spring at rest. So this point right here is where we're going to measure everything from. This is x equals 0. So what happens if you stretch out the spring, to right here, x equals a. So if we stretch out the spring, what is the spring now doing to us? So if you were to stretch out that spring, What is the spring doing? Well, yeah, but it's so I guess really what I should think of is Newton's third law. You're pulling the spring this way, and what's the spring doing in response so that it remains at rest? Yeah, right, exactly. So let's say you pull the spring to x equals a. You're exerting a force to pull it, and the spring is exerting a force to pull back, and they remain at equilibrium, right? And the amount of force with which the spring is pulling back is equal to F of A. Right, because we pulled it to x equals A. So F equals A. Okay, I just want to type that. F equals A is the amount of force exerted by the spring when extended by A meters. Right, does it make sense? Like, it was at rest at x equals 0, you pulled the spring out A meters, and now it's pulling back by some F of A. So that would be F of A, and then the other vector in the other direction would be your pull. Okay. Making sense so far? Okay, now you're wondering, how much work does it take to pull the spring from equilibrium to x equals a? In other words, like, what's the amount of energy I'm gonna have to expend to pull this off? That's what we want to calculate. Now, this is complicated by the fact that the force that the spring exerts is not constant. So let's write that. The force that the spring exerts is not constant. Oops, it's supposed to be a sad face. And explain what I mean by this. So here's your spring at equilibrium. How much force is the spring exerting? If that's the spring at equilibrium. Yeah, 0. Awesome. Let's stretch that spring out a bit. Does everyone agree that now the spring will be exerting some force in that direction now? Because we've expanded a little. It's trying to pull back to its natural equilibrium. So let's just say it's exerting 0.1 newtons of force. And let's say that we stretch out the spring even more. Now it's exerting an even larger force. Like, basically, the spring is like, fuck you, I want to go back to like what I was at. And the more you pull it, the angrier it gets. Yeah, it's a tension force. Well, I wouldn't say that I'm enough of an engineer or a physicist to tell you if it's a tension force or not, because like that might mean a very particular thing. But yeah, I totally get what you're saying. I think it might be a tension force. But does it make sense? I'm just saying, like, I'm not sure because I don't know if tension force might mean something else, like in context, if you were to use the word properly. Yeah. So now your force is something bigger, like, I don't know, it's 0.5 newtons. And you stretch that out even more. You're like, spring, we're stretching you out more, and the spring gets even angrier, and it pulls back even harder. Right, you can see my arrow's getting bigger now. It's like pulling back with like a 1 newton of force or something. I don't know. See, this is the problem. As you stretch out the spring, the force that it exerts becomes greater. In other words, it's not constant. So you can't just like say, oh, the force of the spring is whatever, and then multiply that by the change in distance. That doesn't work. Because the spring gets angrier the more you pull it. So we're wondering, like, well, how are we going to do this? And basically, this is what we're going to do. The total change in distance, because remember it started like right here. It started right there, and then where did we end? All the way over here. Right, does everyone see, like, that was the total change in distance, the total distance the end of the spring moved. I keep on wanting to say string, but it's a spring. Oh, let's turn on the light. There we go. Got some lighting. Okay, so there's that distance. What has always been the idea? If we want to calculate something, how are we going to approximate it? By breaking it up into pieces. Does that make sense? All right, here's our x0, here's our x1, here's our x2, here's our x3, and here's our x4. How far apart are all of these x values? Delta x, yes. So delta x is always that distance between those points. I like that. When in doubt, remod it out. That's basically what this is. Like, this whole class, like Calc 2, can be reduced to, yes, approximate it with a Riemann sum. Yes, take the limit. Yes, you will get an integral. That is basically physics. Which is why this is a prerequisite for physics classes, because they want you to be able to do this. They don't want to have to explain all this crap. So if you look at it, this going from x0 to x1, do you see how that's stretching out this first stretch of the spring? Like, do you see how that distance x0 to x1 is basically that first stretch right there? And then going from x1 to x2, do you see how that was basically the second stretch? So the idea here is that you can break this down like as a sequence of stretches. Instead of just thinking of like a nice continual stretch from here all the way out to here, you can break that down into thinking of it as, first I stretch to here, and then I stretch to here, and then I stretch to here, and then I stretch to here, and you're like, and now I've done all the stretching, right? So instead of like one stretch, you think of it as like a sequence of 4 stretches or something. Okay, now if you think of that, if you look at this first stretch here, from x0 to x1, oops, you can approximate the work done there. So work equals your force times your distance. What was the distance that we stretched it on that first stretch? Like, what was the change in distance of the end of the spring? How far did we stretch it? Yeah, delta x. Nice. So we're like, okay, we stretched it by some amount, delta x. And the problem is that here's x0, here's x1. We stretched it that amount. We know that at x0, you can plug in x0 and get the amount of force that the spring was exerting. And you can plug in x1 and plug in the force that the spring was exerting there. What's the best value that you can use to approximate the force over the whole thing? Yes, the midpoint. And do you see how it's like, it always comes back to this? You're like, fuck it, I don't know, just whatever it was in the middle is a pretty good estimation of what was happening over the whole thing. So you're like, okay, x star, our midpoint, that's a pretty decent estimation of what the force was over the whole thing. So if the work over segment I is equal to f of x star times delta f times delta x, what will the total work be equal to? Approximately. So if that's just the work on one of the segments, what will all of the work add up to? You just take the sigma of that, right? Yeah, exactly. So you do the sigma of all those individual works, which is the same thing as the sigma of f of x star times delta x. And you look at this and what do you basically see? What do we got? We have a Riemann sum. So if this is the estimate for the total work, how will you get what the total work is actually equal to? Well, you'll take the limit as n goes to infinity of this sum of the individual works, which means that what are you going to do to get work? You're going to integrate from a to b your force function dx. Boom. Okay, so this gives you, basically it gives you a formula for setting up. If you ever need to calculate some work, you go back to setting it up like this. You know that you're going to get some integral, definite integral to calculate. Yeah. So actually, we're going to talk about a famous example. So calculus was invented to do all of this. There's no star here because the star is for the midpoint. If you're looking on a particular segment, when you take the integral, you just do integral of f of x. So let me give you an example of how this was discovered and basically why people invented calculus to do all of this. So have we heard of a guy named Robert Hooke? Englishman, contemporary of Newton. Yeah, he was Newton's nemesis. Newton was like a Kirkland brand. Hooke was like the Kirkland Newton. What does that mean? If I call Hooke the Kirkland Newton, like what does that imply? Yeah, he did a lot of cool stuff. Yeah, it's a good deal and it's generic. He doesn't have like all of the brilliance of Newton, but like he got the job done and like everyone's like, yeah, it's pretty good. But yeah, he was Newton's nemesis. He was sort of like a narcissist, just to tell you. Like he felt like he deserved way more credit than he got. He got tons of credit, but whatever. So this is what Robert Hooke did. He did experiments with springs. And actually, one of the reasons he was able to create the barometer is because the barometer is just a very sensitive pressure measurement device or force measurement device. Oh, we only have 5 minutes left? Okay, cool. So this won't take too long. So let's say you have a spring. Okay, and this is the spring at equilibrium. So this is going to be the point from which we measure shit. And this is what Hooke noticed. Let's say that you stretch out the string to x equals 1, and you notice that the force after you stretch it out by 1 meter is equal to 3 newtons. And then he stretched it out some more. He stretched it out by 2 meters. And he noticed that the force when stretched out 2 meters is equal to 6 newtons. And he basically kept doing this. And he's like, okay, I'm going to stretch it out some more. I'm going to stretch it out by 3 meters. And he noticed that when he stretched it out 3 meters, he noticed that the spring was exerting 9 newtons of force. What do you notice about the force function? Like, what seems to be the form? Yeah, it's linear. And basically Hooke's law says that the force, actually let's just type this, there's no point in trying to literally write it out. So Hooke's law says that the force exerted by a spring is proportional to the extension of said spring. In other words, the force, if you extend a spring by some amount x, it's always going to be equal to some constant times x. Right? What's my constant in this example over here? What was my f of x? Yeah, it was 3. So how did they figure this out? They didn't like reason it. He literally just started like screwing around with springs, and he's like, oh wow, this is actually pretty crazy. Like, it's just always linearly proportional to the amount that you extend it by. Which is why he was able to make the barometer, because the barometer just measures the change in force as you, does it make sense? The air is like pushing on the barometer, and that's like a force, and he came up with something that was able to measure very weak forces. Okay, so what happens a lot of the time is that like, when you do like empirical like it's not theoretical physics, they call it experimental physics. Experimental physics is all about like making some device to measure something and then trying to use your math to to figure something out. So you're able to use this to calculate the amount of work that a spring you're going to need to exert to stretch out a spring, because usually a lot of things in the world, the amount of force you apply is proportional to some sort of extension that you're doing. Okay, so I think we'll just end here. We're going to talk about pumping water next time. Yep.